Okay, let's get started. How's everybody doing today? Excellent. That's what I like to hear. You guys excited for some more reinforcement learning?
I don't know, maybe you have more things.
What's that?
Maybe you gotta reinforce it.
Yeah, we'll reinforce the reinforcement learning concepts for maximum knowledge, as per usual. Okay. So, real quick announcements. My office hours tomorrow are canceled. There is a ECE robotics faculty candidate interview happening right now, and so his talk is tomorrow. Actually, this brings up a good point. There are frequently robotics talks and AI talks and data science talks happening on campus. Frequently those are AI adjacent, at least in the robotics field. So I may put up on the announcements kind of links to those. You should definitely attend if you're interested in these topics. It's all, I mean, it's going to be kind of graduate level research generally being presented, but as you learn more in this class, you'll see things that you can relate to in those talks. You kind of get an idea of kind of the state of the art in the fields, etc. It's really valuable. So anyway, no office hours tomorrow, come full circle. If you need to talk urgently and this news disappoints you, send me an email and we can either discuss via email or meet at a different time. Okay, sound good? Awesome. Any questions from last time? Great. Okay, so if you're excited to get back to reinforcement learning, I have some bad news for you. We're going to go over some policy iteration example as per the request last time. So, all right, so the idea is that in policy iteration, we're solving MDPs, right? And so we have this diagram of what MDPs kind of look like from a local perspective down here. You have this state. You have some transition via picking an action to some random other state. I'm about to draw on the board, so that's where that is. So policy iteration is a way to compute a policy, an optimal policy in the limit for some MDP, right? This is in contrast with value iteration, which is another algorithm we've talked about for computing optimal policies for MDPs, but policy iteration is a little different. So the idea here is that first you take some policy. It can come from anywhere. It can be an almost optimal policy. It can be a very suboptimal policy. It can be a random policy, whatever. And you're going to calculate the utilities for that fixed policy for some number of iterations, or until it converges in some sense. And then you're going to improve your policy, right? And so that means we're going to do something that looks like value iteration up here, but with a fixed policy. And then we're going to do one step look ahead here to improve our policy. So we repeat this until the policy converges. Right? So this is frequently better in practice because in policy evaluation, the policy is given to you for most of your steps. So you're not looking over all the possible actions, you're just looking over the one action the policy takes, right? Okay, it's still optimal, and as we mentioned, frequently it can converge much faster than value iteration does under some specific circumstances. So policy iteration is nice from this class perspective because it kind of incorporates a ton of ideas that we've talked about all through MDPs. And so I actually think it's a very good idea to go through a very specific example of how policy iteration works in practice on a kind of simplified example. So if you remember, we have these Bellman update equations, right? This is going to be the value iteration part of the policy evaluation, because our action, remember, is chosen for us by the policy part, right? So we don't have to look over all the actions. But here's the Bellman update for policy evaluation. And then once we have that to a state we're happy with, where we think we've got enough information that we can reason about it, we then go on to the one-step look ahead update of the policy, right? This is all review, right? Okay, so this is about the simplest example I could make for policy iteration that has all of the terms relevant, at least, that we've discussed. Okay, so what's going on here? We've got 4 states, A, B, C, and D. This looks a lot like the grid worlds examples we've been using for MDPs this whole time. And these are our states here. You can see the A's. So here are our transition probabilities, which kind of define our action space. So you can see from A, you can either go right or you can go down. And if you choose to go right with probability 0.9, you will land in B. with probability 0.1, instead you will land in C. Alternatively, if you choose to go down, this probability switch. So basically you get where you're trying to go 0.9% of the time, and 0.1, well not 0.9%, but 90%. 10% of the time you get to the other state. I've simplified it so that there's no notion of going up or left from this state. Similarly, from C, you can either go right or up, but not left or down. Does that make sense? Okay, and so our state space is A through D. Our action space is kind of dictated by the states there. B's action is to leave the game. Similarly with D's action, if you leave from B, that happens always if you're in B. With probability 1, it's your only action available from there. And so we have our transition probabilities shown here. We have here, we have our rewards associated with each of those transitions here. The idea is that every step that doesn't exit the game, you get a negative 0.1 reward. If you exit from B, you get a negative 10, that's bad. If you exit from D, you get a positive 10. And then our discount here, gamma, is 0. Everybody feel good about this? Okay, so that's our MDP, right? So then, it's policy iteration, so we have to start with some policy. Here's our policy. It's a bad policy, right? But it's a policy. Basically, if you're in A, you go right. If you're in C, you go right. If you're in B, you exit. If you're in D, you exit. That's the policy. So we start with some policy. Randomly initialized or chosen to be some nominal values, whatever, right? Okay. And so the idea here is that we're going to do some set of rounds for our value updates under this policy to get a sense for what the values in each state are. Then we're going to use those values to choose a new policy. Does that make sense? Okay. So we're all up to speed. Let's do it. All right. So we have these Bellman updates. They're describing our values with respect to one layer deep's values, right? So we can start at the bottom and say that we know that v sub 0, this is all under pi, right? This is our policy pi. V sub 0 of state A is equal to 0, right? V sub 0 of state B is equal to 0. V sub 0 of C is equal to 0. And V sub 0 of D is equal to 0, right? Because this is how much reward you're going to get if you take 0 more steps. You only get reward when you take a step, so these values are 0, right? Review. Okay, so now what we need to do is we need to figure out for each of these 4 states what V sub 1 under pi is, right? And so we're going to use that expression here. All right, so let's look at what V sub 1 under pi of A is going to be, right? Okay, so our action is defined by the policy, so we don't have to think about all the actions we can take from A at this point, but we do need to take the expected value of the results, right? And so that looks like the sum over the possible outcomes given our action, which is right. And so 2 things can happen if we go right. We can either end up in B or we can end up in C, right? So we need to add those 2 things together weighted by their probabilities, right? So let's say here we end up in A. Let's do capital. Sorry, we end up in B. Yes. Okay, that happens under our policy what percentage of the time?
0.9.
0.9. Okay, so this is our transition probability of being in A, choosing right, and landing in B, right? Okay, so this gets multiplied by the reward we experience for this transition, right, which is negative 0.1, right, plus the what happens if the value from where we land, right, which is B from our previous iteration, which is 0, right, multiplied by our discount factor, which is 0.8, right? Make sense? Okay. But this is just one of our possible outcomes, right? We're summing over all of the possible states. So we need to add here, with probability what, we land in C instead. 0.1. We get our reward for that transition plus our discounted future reward of landing in C, which is 0 in this step, right? So this sum is easy to compute in this case, but what is it? Negative 0.1. Okay, so now we know that V sub 1 under pi of A is negative 0.1, right? Okay, so let's look at what's B? No, B. B basically comes for free. So we start life out in B. What's our expected reward with one step left? Negative 10. So you can do the same math, but this is what it comes out with. It's just one term here with probability 1. You get reward negative 10. Okay. So let's look at C. That one's interesting. Right? So C takes the value. Let's say, all right, so we're going right. So let's say we land in D. That's where we're trying to go. Right? With probability 0.9, that happens. We multiply that by the reward we would experience, plus the discounted future rewards we can expect to get from D, which we have calculated here, 0. Right? Everybody with me so far? Okay, good. We add that to our other potential landing spot, which is A, right? That happens with probability 0.1. We're just reading it off this table, right? So the MDPs generally can be described as some table that looks like this. So 0.1 times the reward that happens with that transition plus our discounted future reward as we've calculated so far. This is B sub 0 of A under pi, which is 0, right? This value is, so far it's pretty easy, right? Okay. So now we have B sub 1 of C, 0.1, negative 0.1, and similar to this. Does anybody want me to see me go through this calculation? No? Okay. Positive 10, right? That's what you really want at the end of the day. Okay. So now what do we do? This doesn't seem like it's enough, right? So let's do it again. It doesn't seem like it really captures the value of the states in a meaningful way, so we'll continue. Okay, so now we want B sub 2 under pi of A, right? Okay, so this is similar to over here. Let's say we land in B. We have to consider both landing in B and in C, right? So we land in B under our policy. What percentage of the time? Right. Okay, and so this is weighting by the probability. We add this to the reward we get for the transition, which is 0.1 plus discounted future rewards. Here, this is now non-zero, right? Negative 10, right? But we need to add to this what happens if we landed in C, right? Which happens with this probability. If that happens, we get our negative 0.1 reward plus our discounted future reward, which is, according to our current estimate. So this is V sub 1 under pi of C, negative 0.1. Okay. This whole quantity here ends up to be roughly negative 7.31. Okay? With me so far? Yes?
That second line, is that saying that the probability that it goes from A to C by moving right is 0.1?
Correct.
How is it possible to move to C by going right?
that's just the way the world works. So there's some stochastic nature to how moving right is, and 90% of the time you end up where you wanted to go, 10% of the time you accidentally go down instead of right.
Okay.
That's just how MDPs work.
This is where we have the chain of problem.
Yeah. This is just,
It's labeled up there on the page.
yeah, so it's just the transition probability. If we knew exactly where we were going to go, we'd have easier ways to solve the problem. But because of some uncertainty in the world, maybe there's winds blowing our robot and it's a boat robot, or our wheels don't work right in the mud or something, we end up where we didn't expect to be, right? Okay, so, exactly. Good? Okay. All right, so we now have an estimate from 2 iterations of this algorithm of v sub a under pi, right? Which is, what did I say, negative 7.31? Okay, now we get for free b, that's just going to be negative 10. Similarly, we get for free d, which is positive 10, right? Because if you have 2 steps left and you're in d, you only have one choice, it's to leave, you get 10, game's over, so there's no other choice, right? Okay, but still, what's interesting to compute is v2 of c, right? Which we need to compute the expected value of, right? So let's say that we land in D. That's where we're trying to go, right? That happens 0.9. The instantaneous reward plus the discounted future reward, which is d sub 1 under pi of d. 10. The other option is that we landed in A on accident. Here's the probability that happens. Instantaneous reward, discounted future reward. What's this value here? Negative 0.1. This is roughly positive 7.10. Okay, so you're already starting to see kind of that being in C under this policy is better than being in A under this policy, right? That puts us, B2 under pi of C then is roughly 7.1.
So is this just infinitely recursive because it's constantly?
Yeah, so the way this algorithm works is it's approaching the true expected values at each of the states as time goes to infinity, as the number of iterations goes to infinity. But we get close pretty quickly. Yes?
Yeah, so we just keep going until the values of each of those are like not changed by some threshold.
That would be a way to choose when to stop this process. You could also say, I'm just going to do it 10 times, 100 times, 1,000 times, kind of depends on your problem. You could have that adapt over time based on some more information about how fast it's converging in a general sense. Yes?
Or maybe in like a real-time situation, if you just, I'm going to spend as much time as I can on this until I have to act.
For instance, exactly. Although in this case, you would want to build in the time allotted for the policy update as well, potentially. But, okay, and the reason this is converging to the true values but not describing the true values is that because of these transition probabilities that are imprecise that we can go up and down, there is with some non-zero chance under a fixed number of time steps, the chance that under this policy we just bounce back and forth between A and C. Right? It's very unlikely for long time steps, but it's non-zero for fixed time steps, right? You see that? Does everybody see why that's the case? So the true values accounts for that infinite sequence of probabilities, right? So we can't really compute that explicitly right now, so we're just converging to it. Does that make sense? Okay. Let's do one more iteration of this. I'll just go fast since I think we've got it, but the numbers become a little more interesting. So if we look at these 3 under pi of A, we could land in B. Or we could land in C. Which is roughly negative 6.73. Okay? So here we can land in D, that's where we're trying to go. Or we could land back in A. This is roughly 6.52. Okay. So you see how, we start with these trivial calculations. We're keeping track of what we've computed at each step. We're using the values we computed at the last step to move forward with the next iteration. Right? That's dynamic programming. Right? So that's why this is an example. All right, let's say, okay, so where did we land? We have, after 3 iterations under pi, d of A is negative 6.73. B of B is negative 10. B of C is positive 6.52. And B of D is 10. Right? So now we have values for all of our states. Let's pretend that these have converged under some definition of convergence. And so now it's time to do the second step up here, which is the policy update. Okay. So what we need to know is what's pi. This will be the first time we do it. We can say that this was pi sub 0. We want pi sub 1. What is our policy for A? We find ourselves in A. We want a new policy for A. Maybe it's the same as the old one, maybe not, right? Okay, so this is the difference between having a fixed policy and not. Now we have to reason over all of the actions and all of the possible outcomes of all of those actions, right? That's what we would have been doing under value iteration the entire time, but because we have this fixed policy, we haven't been reasoning over the possible actions. Yes?
I was gonna ask, so would it be like out of scope to consider like doing what we just did for all 4 steps, but simply for A in all 4 directions, and to determine a better outcome from that?
Well, that's what we're about to do. So you need some notion of how good choosing to go right or down or up or left is from a given state. And so what we've done so far is we've kind of estimated the values of what happens afterwards. You need to know that in order to reason about which action is good, right? And so what we did is we started to estimate the values of the states. Now we're going to say, I'm going to estimate, or I'm going to choose new policies, a new action from each state based on what we calculated last time. So we were learning kind of how good the states are. Now we're going to say, let's update our policy based on what we've learned. Make sense? Yes.
So in this section, we have to consider each direction with respect to the policy element, basically?
We do now, yes. And so it's important to keep in mind that these values that we've computed are a function of the policy. They're not the optimal value. They're not the values that they would be under the optimal policy. These are the values associated with the policy. And you can see through all this calculation, all of these are dependent on the policy, right? So everything so far has depended on the policy. These are with respect to the policy. But the good news is that through some algorithmic magic, it ends up converging to the best policy and the true values with enough time. But in short time, you can get something pretty good, right? Okay. So we need a new policy for the whole MDP. Specifically now, let's see what our new choice of action would be if we find ourselves in A. So now we have to reason over all the possible A's. That's this argmax here of A, right? So argmax is just take the max and return the argument that created that maximum value under the equation on the right, right? So the max would just be a value. That's the value of the best state nearby. But you want the argument that got you there, that's argmax, right? Simple stuff, but you may not have seen it before.
The argument is A.
The argument is the action.
Is the action.
So remember that policies map states to actions. So we can say that pi sub 0 of A was right. Right? And so there's no way that the word, or the action right is going to fall out of some summation. Right? That would be kind of strange. So that's what argmax means. It just says, look over the A's, return the A that produced the maximum value to the right. Right? That's
So when
argmax.
we do this for every state, we don't iterate the policy in one step, we iterate every bit of the policy to iterate.
Yeah, so now we're going to consider all of the states. From all of the states, we're going to consider all of the possible actions. From all of the possible actions, we're going to consider all the possible outcomes. So this is this order S squared A, right? All the states S, all the actions A, you multiply them together, right? And then S again. Yes?
So we're basically just doing a value iteration step for use of.
It is similar to a value iteration step in complexity. The equation is almost the same except for we're changing the policy.
Yeah.
But yeah. Okay. So we want, that was pi sub 0 of A. We want pi sub 1. So what is that? The argmax. Okay, so let's consider, so we need to reason over all the possible actions. So let's reason over right first. What happens if we go right? Well, this is going to look very similar. It's basically what we were just doing. So you might land in B. This is exactly what we did. It's just another step. This is not news, right? This is what we've been doing all day. Right? These values are being pulled from here and here, respectively. Right? Okay. This is so if we look at going right, this is the value we can expect from having made that decision. Right? Well, we're doing the policy update now, so let's consider, we only have two options from A. We can go right or we can go down. Right? So let's look at what down looks like. So what happens if we choose to go down? Well, now it's different, right? We might land in B still, but the probability changes, right? Because that's not where we're trying to go. So now it's 0.1 plus the instantaneous reward of what happens there times the negative, times the instantaneous reward plus the value of the future, right? Alternatively, we could land in C, which is where we're trying to go. Subsequently, the probability is higher. And buy higher quality chocolates. This is roughly 3.79. Okay. So for state A, we've reasoned over all the possible actions and all the possible outcomes, right? So what do? We picked the best one, the argument that produced the best value here, right, which is down. So now pi sub 1 of A down, right?
So in these calculations, our best understanding of what we did from the policy
Exactly. Yeah, so these were the values associated with landing in, this one's C, from, where were we considering A, right?
That's what allows us to do that one step.
These values aren't the correct values under the new policy, right? Because we're defining the new policy. These are the values under the old policy, which is slightly different. But it's more information than we had before, and we're just going to keep building on the information as we go. Right? Yes.
Would it be possible to like cache these values or add like a heuristic so that way we can save ourselves calculation for like future iterations?
So we should always be keeping track of values that we've computed and leveraging them in the future when they appear exactly again. So that's the dynamic programming aspect of it, right? The question becomes maybe, what do you do once you have a new policy? Like in a second, we'll compute the new policy for C. Then we have a new policy across the board for all the states we care about. What do you do now? Because now we're going to do value iteration under the new policy.
We just do the same thing we did with the first policy.
You do the same thing you did for the first policy, but the question is, how do you initialize it? Naively, you would set them all to 0 there, right? But maybe that's the wrong answer. Maybe you would want to instead use the old values. Because maybe if your policy didn't change a lot, they're pretty similar to what they need to be. Your convergence happens faster, potentially. That's like a heuristic decision based on this kind of stuff, right? Where you keep these values around. Does that answer your question?
Yes.
Cool. Okay, so that was pi sub 1 of A. We can do the same thing of C. Pi sub 1 of B and pi sub 1 of D are trivial, right? There's only one option from those, and that's to exit the game, right? Okay, so I'm going to go fast again here, but we have to reason over all of our possible outcomes, or all of our possible actions. So from C, we choose to go right. Now we have to reason over all the possible outcomes of this decision, right? So let's say that we land in D. That's where we're trying to go. I'm going through this so that you have it at home in the videos if you want to review this later. But this is what happens if you're in C, you choose right, you go to D, but you might instead end up in A, right? And so if that happens, that's not where you're trying to go. Happens with a lower probability. That value is being pulled from here, right? From the old policy. Alternatively, you can choose to go up. We have to consider them both. If you choose to go up, you might end up in D, improbably, but it's possible. You might instead end up in A. That's where you're trying to go. Oh, it gets hard down here. 6.73, right? Negative. Everybody see it? So this is roughly 6.56. This is roughly negative 4.15. So what is our new policy for C? So now we have updated this. There's a new policy. Right. Yes.
So the values we preserve for the next step of like the BC pay stuff, is that like the policy values that we selected? So like for A, the value we assigned to B sub A 0, is the B sub A where we're at 3 will be like 3.79 versus negative 6.78 because we changed the policy?
That's up to you. It's not clear to me that that's the right answer. It might be though. These are all kind of reinitializing the valuations. It's kind of a heuristic decision.
Okay.
Different strategies are going to be better in different settings. It kind of depends. I know that's the answer I give a lot in this class, right? Like, it depends on the problem.
Yeah.
But that's because we're solving hard problems, right? So there's never a clean, easy-cut answer. Yes?
Yeah, for robots that are doing, like, say that's following this path, is this done beforehand, or is it done on the fly, or does it depend on culture?
So this is, because we're given all of these parameters, we can reason about the whole state of possible outcomes and actions in advance. So if you have your transition probabilities and your rewards, it's an MDP, you plan offline, you produce a policy, then you just apply that policy, right? The difference between this and reinforcement learning is that now you have to actually, in reinforcement learning, go try things, see what happens. There's a lot of parallels, right? But that's the difference. So this is happening offline. Does that make sense? Yes?
Is there any kind of analogous quality to consistency when it comes to deciding how you're going to reinitialize to kind of estimate how this change in your policy will affect the values you've already computed? Is there any kind of quantity that you could say, like, if it's less than this or if it is within this bound, then it's guaranteed to not propagate and create an error later?
That's a very interesting question. Yeah, so I don't know, but there's a ton of work. This is the basic policy iteration algorithm. There's been a ton of work in making this better by informing these decisions as you go, adapting these decisions over iterations of the algorithm, looking at quantities, proving things about what's going to happen downstream in the algorithm, things like this. So I don't know offhand, but it wouldn't surprise me if there were ways to do that in SMART. We are going to see something that's a little bit related to consistency here in a minute in reinforcement learning, but yes.
So just checking my understanding, so for each state, right, we're choosing which way to go. And when we iterate through the policy, right, the meaning of going that way is completely contingent on the fact that we're doing a new policy. So we can't like reuse that same value, say we're going right at C in a new policy because it might be different.
Yeah, so you're going to have to re-update these things. But it might be a good initialization, right?
Yeah.
But you're going to then have to go back and recompute the values because the values are a function of the policy.
In terms of a new policy, would that also include like different percentages or possibilities in the direction you try?
No. So the percentages, the possibilities, all of this is fixed in advance. That's defining the MDP. What is changing is kind of the order in which you're reasoning about them because your decision changes, which is more likely based on the possible outcomes of your decision. But the set of state, action, outcome, probability tuples is fixed in advance. Okay. If we feel good, we could move on back to reinforcement learning. But this illustrated a ton of very interesting concepts that kind of summarized MDPs, right? This is the simplest MDP I could come up with that was trivial, but still contained all the relevant parameters like a discount and probabilities that weren't one, etc. It's a giant pain, right? Even solving this extremely trivial MDP by hand, not super fun. So this is why it's important to be efficient in your computation. Make sense? Cool. Okay, but now, were we to live in this 4-block world, we would have a better idea of how to avoid the red square of awful and instead end up in the green square of niceness, right? Seems valuable to me. Okay. Let's then let's take a break. Let's take 5 minutes while I set up, and then we will get back to reinforcement learning. Sound good? Let me just start my timer. I won't forget. And then we'll have a break. Oh, sure. Boarded.
So we have these defined parameters. Things change in the real world. Is there like an additional level of abstraction we can add? Like, oh, there's also 50% probability that the probability of being here is going to be different. Yes. Or at that point, it's just too complicated to be using abstraction.
Well, it gets pretty complicated.
Already it's pretty complicated.
Yeah. So if we had some higher order notion of probability, to use the techniques we've talked about now, we would have to frame that unseen problem, which I think you could do. Okay, it would just be kind of a complicated.
Yeah, I'm not doing it by hand.
Certainly, but I'm not doing any MDP by hand.
Oh, sure. But also,
So they're deficient. So, no, but it's important to it's really important for understanding MDPs to kind of know how to work through that process yourself. And so we may have you do something simpler. Yeah, it's just easy that you start messing up early and the errors cascade down, and that's not good. So we'll see. But yeah, good question. Okay, let's get started. All right, so moving on from these Markov decision processes, MDPs, to reinforcement learning, which is very, very related. Moving back to reinforcement learning, who can tell me again what the difference between the two was? There's one big kind of key conceptual difference.
You know the probability of the Markov? You have to figure it out.
Yeah, you know both the transition probabilities and the rewards. in reinforcement learning, you may know, right? So, to motivate that it's not all grids, remember that this is the kind of algorithm that can allow us to look at complicated behavior learned by robots, such as the snake robot kind of hopping itself up onto this table. Right, so this wasn't hand programmed in at all, it was learned behavior by the robot using reinforcement learning. Or this toddler robot learning to walk around. Right, yes?
Do you know how the snake detected whether or not it was on the platform, or was it using a?
I'm not sure, I think they had a vision system, but I'm not positive. Reinforcement learning, right? So we still assume a Markov decision process where we have states, actions, some models, and some rewards, and we're looking for a policy. But now we don't know T or R necessarily. So if we take this MDP that we had worked with in the past about overheating our car, this is the new state information. So we had talked about this notion of offline versus online computation. Right? When we were solving MDPs, we have enough information that we can reason in advance about what we should be doing. In reinforcement learning, we don't. So we have to go try things out, right? And so this agent may not know in advance that jumping off this cliff into the fiery pit is a bad thing, so may have to do so. This is frequently done in robotics, and it's important to note that if you're working with real robots, jumping off of cliffs into pits of fire can be expensive. So, both in terms of your money and the grad students that have to rebuild the robot or whatever, right? So, that is frequently done in some simulated environment, right? But it's still different from reasoning in advance because you have to actually step through these simulations to see what's happening, right? So, offline learning can happen. Offline learning just happens with some problem formulation you reason about in advance. Online learning can either happen in simulation or the real world, wherein you're sensing things that happen. But either way, there's this notion of exploring the possible outcomes, right? Okay, and so we talked about model-based learning, right? That's where we're learning explicitly these transition functions and the reward functions or some approximation there, right? And so once we have those values, then we can solve the MDP using the same algorithm that we just did on the board, for instance, right? So we had this example, right, where we just observe. We have this grid world again. We have A and D. These may have rewards. There may be transition probabilities. We don't know what they are. But we did see 4 instances of an agent moving through this world. Either we collected that data or we observed it happening something, right? And so then we can say, based on the outcomes that we saw, the frequency of the outcomes that we saw, we can construct explicit probabilities as well as the rewards that we accumulated, right? So we build this model, this matches the MDP that we had, that we can solve this MDP using whatever. So that's model-based learning, and we'll touch on that later in the next couple weeks, but we're going to move on to now to model-free learning. And so to kind of motivate the difference, we're going to talk about, say, computing the expected age of all of you, right? So let's say that we know the probability. We know the probability that if we sample one of you, your age is 24, let's say, right? Then we can compute the expected value, right? And we just get, at the end of the day, the expected value of the age of the class, right? But let's say we don't know the probabilities. Well, instead we can collect samples, right? So we can say, pull some number of you for your age. We can construct this probability using the frequencies, right? We have the number of times we saw the age 24 over the total number of samples, right? This gives us our approximate probability. And then we can go and compute our expected value using this approximate probability, right? And this is approximate because you see this hat here. Oh, the pencil's not working again. Okay, there's that hat, right? Approximate. All right, so that's kind of the model-based way to think about this, in that we're considering explicitly the probabilities thereof. But there's another way to do it. We can do it model-free. And that's where we just say, let's average the age. Let's poll. We'll just do the average, right? These are the same thing. Right? You can can go through the algebra, they're literally the same thing. But in one sense, you're kind of reasoning over what the probabilities are explicitly, and in the other, you're just using the fact that when you poll the class, you're sampling from the true distribution, right? So here you sample at random, you construct an approximation of the distribution, and you reason over that. In the other one, you notice, as I sample, the distribution's represented there in the sampling process. I don't need to reason over it explicitly, I can just average over the samples, right? That's kind of the difference. So this brings up model-free learning. All right, so we're going to talk now about passive reinforcement learning. So this is a type of model-free yes?
Doesn't that assume a uniform distribution of the ages? Like if everyone in here was either 21 or 24, we would sort of guess like 22 and 23 that there could be no one with that actual age.
So it does assume a Gaussian distribution, I believe, probably. I need to think about it a little more, but yeah, it's bimodal distribution. Well, but the expected value is sleeves. So no, I don't think it needs that assumption. I'll think about it more and bring you a certain answer next time. So. Okay. Model-free learning. So under model-free learning, there's a class called passive reinforcement learning. So passive reinforcement learning is where you're just watching some agent move through the world, kind of taking notes and learning the best policy that you can reason about from your observations of the model, of the agent moving through the world. The alternative would be active, in which you're making decisions as the agent, as you reason about the policy. Does that make sense? Okay, so let's talk about passive reinforcement learning. So this is a little bit simplified in the same way that policy iteration was kind of a simplified concept. Yes?
Is it a lot like supervised learning?
Supervised learning is a subset of machine learning in which you have labeled data.
It looked like he was watching like a video game, I guess. That's what I did think. So,
So
it's like showing examples to the model that we're trying to build and then using those as training.
in that sense, it is kind of like supervised learning. But I would really
Try to separate them.
try to keep these two things distinct. Okay, so it's kind of a simplified task, right? Because we're not reasoning over actions, what actions we can take, we just watch the actions that we're taking, right? And so that means that there's some fixed policy, we don't know the transitions of the rewards, our goal is to learn the state values, right? In this case, our learner is along for the ride, so you're not making any choices about the actions, you're just executing the policy or watching the policy be executed and learning from the experience. Again, though, this is not offline planning, right? Because there is some agent that has to move through the world in order to experience the world and learn from it, right? Okay, so a way to solve the passive reinforcement learning problem would be something called direct evaluation. So we're kind of getting deep in this tree of types of reinforcement learning, but it all, like the whole taxonomy, will kind of become clear as we move through this semester. Okay, so let's talk about direct evaluation. So the idea here is that we're going to compute the values for each state under pi, and then we're just going to average together what we observed, right? So we act according to pi. Every time we visit a state, we write down what the sum of discounted rewards turned out to be, and we average it, right? This is direct evaluation. So let's look at an example. Okay, so here's our policy, and we observe these 4 episodes, right? So we either acted according to the policy and wrote down what happened, or we observed the agent acting under the policy and wrote down what happened. But we were just executing the policy, we weren't reasoning about better policies as we did it. All right, so then what we want to come up with are the values associated with each of these, right? So we can look at how many times did I see A, and what happened when I saw A, right? Oh, I really wish my pen was working. So we saw A once, and we got a value of -10, so that averages out to -10. We can do the same for all the times we saw C, all the times we saw D, all the times we saw B, and just average out the expected reward, the total reward over the episodes that we saw when at some point we started out in the state, right? So E's kind of interesting, right? Here we started out in E, we ended up going north into C, we went to D and exited and got a total of 8. Here we started out in E, because of the randomness of the system, we ended up getting a reward of negative 12. Right? So we average those two things together, we get negative 2 for E. We can do the same thing for C. It ends up being positive 4, for B, positive 8, etc. Right? And so now we have some estimate of the values associated with each state, right? It's just what we saw. Right? That was the value associated, the average value associated with what happened when we saw an agent start in that state and run through the end of this. Okay. But there's something kind of missing here, right? A lot of this doesn't actually seem to make sense because there's structure in this problem that's not being leveraged in the computation. And you can kind of see that manifest here in some specific ways, right? Does it make sense that E would have a value of negative 2 and B would have a value of positive 8 when both of them have to go through C? Once you're in C, it doesn't matter where you've been, right? That's the Markovian property. So these should really be the same as long as the transition rewards associated with this transition is the same. But they're not, right? They're very different. Similarly, it doesn't make any sense that you would start in a place that you think is worth negative 2-ish, and then immediately transition to something that's worth positive 4. That doesn't make any sense, right? That's kind of like inconsistency in our heuristics when we're looking at A star, right? So maybe there's a better way. Does everybody see why this is not the same as the model-based learning where we were explicitly constructing the probabilities? There's like nuance here, but basically we're just assuming that what we observe happens as a function of the true distribution, right? Rather than trying to model it explicitly. Okay, so what's good about this? Well, it's easy to understand, right? We looked at a pretty simple example. I didn't even get to write anything on the slide, but we kind of get to see what's happening. It doesn't require any knowledge of T or R, and eventually it'll compute the correct average values, just using the sample transitions. What's bad though? As I mentioned, it's kind of wasting this information that we can see, that we know from the state transitions. We have to learn each state separately, so it kind of takes a long time to learn. Eventually this will converge to the right things. If we see enough samples, right? But for now we're not leveraging that structure that we know is inherent in the problem. Why don't we use something like policy evaluation? Each round will replace B with our one-step look ahead that we get from our samples, and we'll just improve our policy as we go, right? So we have 0, this is the Bellman equations, or the Bellman update, right, that we were working with earlier. We just use this, right? Yes?
What does it mean by each round?
I'm sorry?
What does it mean by each round?
So each round would be, well, in this case, probably each observation, each time you see a sample, or maybe each round of some batch set of samples.
Each time you have an opportunity to maybe change your policy.
For instance. What's in this equation that we don't have though anymore? Yeah, we can't use this, right? Because we don't know T and we don't know Y. It would fully exploit the connections between the states, but we don't have the information we need to do. Yes.
So could we do a direct evaluation as your first step? Then you would have some subset T and R kind of pre-computed, and then go off that base point, and then start using this.
So that would be like a model-based approach, right? Where you're estimating T and R explicitly and then you use it later. Yeah, I think that sounds reasonable. There might be an algorithm similar to that. But for now, let's ask the question, how do we do this update, the Bellman update, without knowing T and R? Or what you described as kind of taking the weighted average. How do we do this without taking the weighted average if we don't know weight? So the idea then would be we could take samples of our outcomes by actually doing the action and then average the results, right? So we could take a sample and we could see what reward we got, right? We're doing this iterative process, so we have some building estimate, right, that we're leveraging using dynamic programming. But we use our sample to replace this value, right? We do this sampling process multiple times, starting at S. So we're computing the value for S, right? So we execute our policy pi, right? And then we see what happens, right? We just see what happens once. That's sample 1. We see what happens the second time. That's sample 2. Maybe in sample 2 we end up in S2 prime instead of S1 prime, right? But not necessarily. Maybe in sample 3, we're again ending up in S2 prime, and that's because we're drawing these samples from some underlying distribution, right, that we don't know. But we gather some number of samples, and then we can just say, oh, let's average them, right? We're assuming they were drawn from the true distribution, so we'll just average them. That'll be our update, right? So that is a good idea. The problem is, though, that in order to do so, we have to draw samples from S. That means you have to get back to S under the same conditions over and over and over and over, right? So if you think about working with a real robot in the real world, say you want to learn how this robot actually rolls on carpet or something, that means you have to pick up the robot, put it back at the starting at S, and draw some number of samples, right? And each time you have to put it back exactly in the same state. And do it again. You have to do this for every state. That might be possible if you're working in simulation, if your simulation is simple enough where you can guarantee that all of your conditions are the same every iteration, but it might not, right? So the idea instead is, let's say that we take something similar to this, and instead of requiring that we draw samples from S, we're just going to look at full kind of paths, full trajectories through this model, and we'll just get information as we go based on what's actually happening, but we're not going to require them to all be from the same state over and over again, right? Okay, so that concept brings us to temporal difference learning. So the idea here is that we're just going to learn from every experience. We're not going to require that the experiences be starting in the same spot. We're just going to see what happens, learn from every experience, right? And so every time we experience a transition, we're going to update from S, we're going to update B sub S, right? And we know that our likely outcomes S prime are going to contribute updates more often because, again, we're inherent in this simulation process sampling from some underlying distribution, right? And so we still have a fixed policy, we're still doing evaluations, but we're going to use some concept of like running average to get these values, an estimate of these values. We can't do a regular average, right, because we don't know the total number of samples that we're going to end up with. Because we may revisit S in the future and get another sample from S. We don't know in advance how many times that's going to happen over our observations. So we have to have this notion of like a running average, right? This like running update that just gets better and better as we see more samples, but isn't tied to knowing what the true number of samples will be in the beginning, right? Because if we look down here, we need this n, right? So if we don't know n, this is what we're going to do. We're going to weight our new sample with some value alpha between 0 and 1, and we're going to blend it in some sense, some weighted sense with what we already had at that state. So each time we get a sample from S, we're going to take that sample and we're going to combine it with what we've already computed for S under some weighting, right? And so equivalently, you could write this as this, which might be more intuitive, but we take our value that we have estimated at S, and then we add to it some correction, right? And that correction is based on some weight of what we see compared to what we expected, right? Does this make sense? So in this case, as we see more and more samples, we're going to be updating this value. It's going to get closer and closer to what is actually happening under some assumptions about alpha. If we decrease alpha over time in a specific way, this type of running update will converge to the true value. So don't worry about the specifics for how that happens yet, but just take my word for it. But does this make sense? Okay. So we're calling this some kind of moving average, right? And basically, more formally, it's going to look like this, right? And so the implication here is that more recent samples are going to be more important, right? Because we have this kind of vanishing influence of our old samples. It's like this sliding window type thing, right? Yes?
Is this similar, again, bringing, I
So it kind of decays. There's some similarities.
Well, I mean, like just A is similar to like our gamma previously with the update function, where you're reducing A as you reduce.
Right, so here, we're going to have some schedule that we're reducing alpha for in practice to guarantee that we converge to the true solution. But let's just pretend alpha is some fixed value less than 1 but greater than 0 for now. And you can kind of see that your more recent ones are going to be weighted higher. And so with some kind of algebraic manipulation, if you expand this term out forever, this is what you end up with. And so what you see then is that as your x gets further in the past, n minus 2, n minus 3, n minus 4, you get weighted by this value here, which is less than 1, that's being, this decaying exponential, right? So samples that you took long in the past influence this value less than samples that are happening more recently, right? So is that a bad thing?
So I was gonna ask, how does this compare to something like machine learning, where they
So
basically process that?
reinforcement learning is a type of machine learning algorithm. So machine learning is this huge umbrella term. Reinforcement learning is a type of machine learning. Like a subset. Yes?
I mean, like, it depends on how much you do this update. So if you're continuously updating, that decay is going to slowly converge to a point where you're updating less and less, and we're kind of assuming that the path we take right away is like going to happen more often. It's almost like, I think you're assuming a little bit of the distribution here, but the further you go into this, the closer you're going to get and converge despite the limited updates. And it's probably good to not keep the same value in the update, because then you might be flip-flopping policy constantly. And so the decay is kind of used to converge to something.
Yeah. Yeah. So intuitively, the idea is that early iterations of this, we have this kind of unstable estimate of the value. We had only seen a couple samples. It's probably not a very good estimate, right? But as we go, as we see more and more and more samples, we assume that this value gets kind of better and better over time, which we can guarantee under some assumptions. Then those first values were bad. We don't want to weight them highly anymore, right? So it's not really, I'm not going to say it's always good to not weight old values highly. That's not the case, but the intuition here is that it's actually a good thing, because your older values were less stable, they were less correct, less close to the correct value probably, etc. Right? Okay, so this kind of forgets about the past, and this is the intuition I was describing. Those distant past values were probably wrong, so let's forget a minute. Right? Okay, and as I mentioned, if we decrease this alpha, which we're going to call a learning rate, in a specific way, that we can prove this converges to the true edge. Okay, so what might this look like? So again, here's what we've got. Let's assume that our discount is 1, so it's not being discounted. Our learning rate is 1/2. And this is what we've got. So these are our current estimates. And we're going to watch this agent as the red dot move through this, and we're going to update our values as we go. Right? So we start in B, we're going to choose east, we're going to go to C, where you get an update of -2, a reward of -2 from this transition. Okay. So here's our new Bellman equations, but basically that -2 gets weighted in. Alpha is 1/2, so we take our previous estimate plus 1/2, what we just saw happen, right? We ended up in S prime. This value was 0, right? So this term is nothing. This is the reward we got, -2, right? Weighted 0.5. You get -1, right? Did everybody see that? Okay. This is like the 34th version of the Bellman update equations we've seen. Right? They're all just different enough to confuse everybody. So similar, sort of. That's why it's really, really, I mentioned this last time and maybe the time before, it's really important to have intuitive understanding of what the Bellman equations mean, what they're doing. So that you don't need to memorize the very subtle differences associated with every relationship we're defining. You can derive them based on your understanding of how the equation works, right? Okay, anyway, side note. All right, so let's say from there we choose east, that's our policy. We end up in D, we get a reward of -2. What's this value going to become? What's our v sub pi of c going to be?
-3.
Let's see, maybe. So you're faster at the math in your head than I am, if that's true. So this is nothing, right? Because v sub pi of s is 0 here still, right? So the reward we're going to get is -2 plus gamma. Gamma was 1, right? Times our estimated value from s prime, which here is 8, right? So this is 8 minus 2 times 0.5. Did you say 3?
Yeah.
Nice. Yes.
3.
And on, right? So values over here are kind of influencing the values adjacent to them in a way consistent with what the Bellman equations mean. And then we're updating our current estimate as we see new things happen, right? Okay, so what are the problems here? So kind of as a summary, it's a model-free way to do policy evaluation. It kind of mimics these Bellman updates with some notion of running averages. But if we want to turn our values into a new policy, how would we do so? If we do this one step of kind of policy evaluation, similar to what we were doing earlier, then we have to start reasoning over these values again, right? But that's the model. We had been model free until now. So what do we do? This is the idea that kind of changed reinforcement learning recently and caused kind of the rebirth of this. The idea is that we're going to learn the Q values instead of the values, right? So we have an estimate of the Q values, we get the policy for free, right? It's just the Q value that's best. Right? So the idea here is that we're going to learn the Q values instead. That makes, as I mentioned, the action selection model free as well. Right? So this brings us to active reinforcement learning. So now, instead of just following some policy, we're going to start updating our policy based on what we've learned so far, making better and better decisions, exploiting the information we have about the world, while also exploring new parts of the world we haven't explored sufficiently in order to have the information we need to reason over that. Right? Okay. So again, we don't know the transitions, we don't know the rewards, but now we're choosing the actions. So our goal then becomes to learn the optimal policy, or similarly the values. Yes?
Actually, this is kind of a complex question. I'll probably wait till after.
Okay. Okay. So in this case, the agent that's learning is also making choices, right? And so now we can start to blend this notion of exploring our environment with exploiting the knowledge we've already gained about it. And so there's this fundamental trade-off here, right? So we saw this with our slot machine example last class. At some point, you need to stop learning so that you can actually make good decisions based on what you've learned so far, right? That's hard to decide. No, just keep playing the bad one. I'm with you. But again, don't go to Vegas with that. So, I want to reiterate this. This is not offline planning. We are taking actions in the world or a simulation of the world and seeing what happens. Right? Okay, so let's talk about Q value iteration. So the idea here is that we're going to start with 0. This is very similar to what we're doing with regular value iteration, right? And given our knowledge, we're going to calculate the depth for one more. Right? Looks like this. But we're going to estimate the Q values instead. So we start with Q, given that you have no options left, right? That's going to be 0. Given a QK, we calculate the depth K plus 1. Dynamic programming again for all of our Q states. Now the Q states again are the state and action pairs. Right? So there's more of these than the number of states. But if it's still a manageable number, this is a good way to do it. So what do the Bellman updates look like? Here's the 35th example of these. What do the Bellman updates look like if you're talking about the Q values. Okay, so we're in a state, we've chosen an action, so we have to reason about the expected outcome, right? Because some probabilistic thing is about to happen, right? That's weighted by its probability. And then we have, similarly, the reward we're going to experience right now, plus some discount over acting optimally in the future. But from the Q values perspective, acting optimally in the future is the max action, right? It's the best action from that state. So you land in some state, then we need to look at the Q values so you max over the actions. Does that make sense? All right, so the very interesting part about this is that if you looked up here, we had this max in the front, right? So we were drawing samples from the system here, right? But we can't really reason over those because we have this max. But if we push that max deeper into the equation, then we can start to reason over the system using the sample again. All right, so we arrived at Q-learning, one of the canonical reinforcement learning algorithms. So the idea here is that we're going to draw samples of Q values, and we're going to use it to update our knowledge of Q values in the system. So you learn these Q values as you go by receiving a sample, very similar. You consider your old estimate, you weight it against your new estimate. This is what a sample would represent mathematically, right? And so you incorporate that new estimate into the running average. The equation looks like this. Very, very similar, but subtly different in that now we're talking about Q states, which is really important. Okay, so let's look at an example of how that would work. Let's look here. So we're going to watch somebody else move through this simulation. So if we start here, we don't know anything about the world, right? No values anywhere. So it's just moving around. Gets to that state, oh, that was a good one, right? But you'll notice that all the Q values are still 0 everywhere, right? Except for that's the Q value for leaving from that node. So as we transition from here to here, now we have information. This information from this Q value has propagated backwards to this Q value here, right? But there's nothing earlier. So then you can see as we go on and on and on that this information is propagating back in the path, in the trajectory. So what happens now? Well, now we've explored a new state. It's bad, right? In that first one, we learned that this was bad. In the second one, we learned that jumping over here is bad. But notice something interesting. These values are going up. This is the only one going down, right? And why is that?
It's more and more sure that going that direction will successfully bring it towards.
Yeah, because we're propagating this information backwards. We know, based on our previous runs, that something good is possible from here, right? And we're maxing over these values. So this is the value of this Q state because the max here is bad, right? But the information we know about this being a good place to be because we have an option to exit into a nice place is important information, and it's still propagating backwards, right? That's still a good place to be. So we have good options, right? That's what that's telling me. Okay, and let's look at one more example. So we showed you this crawler bot last time, right? So the idea is that we have this box, it's got these two arms, each one can rotate, right? And it wants to learn how to crawl across the screen. So here we have its state space. Remember the first day or the second day, I guess it was the second day when I drew this two-dimensional thing for this robot that had two rotational links, right? Where one is the one angle, the other is the other. Anyway, that's what's going on here. So this is the state space. This is the Q value for each of the states. And it's learning by updating these values as it goes on, seeing how the thing progresses. So if they lower the learning rate, which is what's happening now, this is the behavior. It's learning. Right, so we have this loop, right, that's going through, earning positive reward as it kind of moves along the screen. And that's what it learned through Q learning. So one important thing to note about Q learning, then I'll let you go, it converges to the optimal policy even if you're observing and acting in a suboptimal way. So that's really important. You're not learning about your policy, you're learning about the optimal policy. Okay? You have to explore enough, eventually you have to make the learning rate small enough, but not too quickly. But in the limit, you get the optimal values. Okay, I'll see you guys next time.